Hi class, we are on to section 9.2, Runge-Kutta Methods. So this is sort of the more common method that you'll see for numerical methods. So we'll basically learn how they work and how they relate to the methods in section 9.1. Okay. So Runge-Kutta methods are basically Euler methods, but with a weighted average taken along each interval of our iteration. Okay, so from xn to xn plus 1, so from the value that we're at to the value we want to do next on our iteration, we're just gonna kind of break the value up along a weighted average. Okay, so here we have our next value equaling our current value plus our step size times a weighted average. Okay, so W1, W2, and up to Wm is our weights. Okay, now these weights shouldn't add up to more than 1, right? So it's basically breaking it down into a percentage, right? So if I wanted it to be broken up equally, I would divide, this would be 1 over, since there's m of them, a value of 1 over m, 1 over m, 1 over m, 1 over m, 1 over, and so forth, right? If I wanted to, I can break it up so it's not even, but when I add them all up, they have to add up to 1 or 100%, right? So it can't, the weights can't obviously change the values, right? So otherwise, our values wouldn't come out very well, okay? So here, m is called the order of the method. So the number of weights that I have is the order of our method, right? So if m is 1, that means I only have one weight, and if I let that weighted average value be 1, right? So there's just one of them, and its value is 1. Then my k1 will be f of x and yn, okay? And what I'll get is that my next value is my current value plus my my step size times my function. This is just the Euler's method, okay? Euler's method is a first order Runge-Kutta method because I only have 1, right? M is the order. There's only one value. It's a first order Runge-Kutta method. Notice also, right, I'll just say this now, it shows up later in the video, but remember what the global big O value was for Euler's. It was 1, okay? Improved Euler's method is a second order Runge-Kutta method. Do you remember what its big O value was for its global truncation error? It was 2. Okay, see a pattern coming? So again, hence the big O h squared and big O h3 local truncation errors, right? So again, Euler's had h squared, and improved Euler's was h cubed, but their global truncation errors were big O h for Euler's, okay, and big O h squared for improved Euler's. And again, notice that improved Euler's is the second order, matches with its big O notation, and Euler's was the first order, and matches with its big O as well. Okay. A generalized form for a second order Runge-Kutta method is something that looks like this. Okay, so my next value is my current value plus my step size times some weighted values of that I'm taking, right? So W1 and W2 being those weights, K1 and K2 being those functions, okay? My function, basically. So here K1 is my function, and K2 is my function at some step size h away from my current value, and my current output plus some constant multiple times h times that K1, okay? So for improved Euler's, if we let W1 be the same value as the second weight, equal 1/2, so I'm basically splitting them both into half, I get a value of alpha of 1 over 2 W2, which equals 1, right? This is basically 1/2. 2 over here is times 1/2, right? So they're both 1/2. 2 times 1/2 gives us 1, so that's 1 over 1. That's 1, right? Beta will be the same thing, so that's also 1. So my K2 function is some step size away, step size being 1, so 1h away, or xn plus 1. And then this is going to be just my yn plus, again, beta is 1, so that's h times k1. Remember, k1 was just Euler's formula, okay? So that's going to be, again, xn plus 1, yn plus h. Remember, k1 was my current value plugged into my function, right? And so what's this? Well, when I plug it into everything, right, I can call this, right, I'm looking at the next value, right, of what I would have. So that's f of xn plus 1 and y star n plus 1. So I get y sub n plus my step size. Again, my weight is 1/2 times my current point evaluated in Euler's form, plus, again here, W2 is a weight of 1/2 times my function evaluated at what would be my next point, right? And so what is that? That's just improved Euler's form, right? That's what we had from 9.1. Okay, so that's us over there kind of verifying. So we'll skip the third order Runge-Kutta method, and we'll go straight to the fourth order method. Okay, so here we have yn plus 1, yn plus our step size, k1, k2, k3, k4, right, with 4 weights, fourth order Runge-Kutta method, right? So here k1 is just my standard function evaluated at my current point. K2 is a step size of h away, some constant multiple of h away from my current point. And then yn is something similar, right? Yn plus some constant multiple times my step size times this first function, right? K3 is some other distance away from h. It could be the same as a1, it could be different. Yn is very similar to what we have here, right? Some constant multiple of k1 plus some other constant beta 3 times my step size times this whole function. And then k4 is the same thing, right? K4, the y value, what you're adding to it, is some constant multiple of k1, some constant multiple of k2, and some constant multiple of k3, all being multiplied by your step size, right? The most common form, right? So this is any fourth order, okay? We have a common fourth order that is known as the fourth order Runge-Kutta method, or also as the classical Runge-Kutta method, or just known as RK4, okay? And so these values for alpha, beta, etc. look like such, okay? So they don't all have a value of 1/6, but K1 and K4 is 1/6. K2 and K3 is 1/3. So we can keep the whole numbers here and pull out the common value of 1/6 out. Okay. So here for those alpha 1, beta 1, alpha 1 through 4, beta 1 through 4, this is what we have. So some of them are 0, some of them are not, right? So K1 is just my current point plugged into my y prime function. Here I have 1/2 h away and 1/2 times h times my k1 plus my yn. Same thing here, but times the k2. And then, so the k2 and k3s are the same distance away. K4 is a full step size away. Okay. Truncation errors for RK4 method. So since RK4 is a fourth order method, our error can be bounded by the fifth derivative, okay, in the Taylor expansion. So k plus 1, the k plus 1th derivative term in the Taylor expansion, right? So when we take these values and instead of x minus a, right, taking those substitutions that we had, which was x of n plus 1 and xn, that turns into our h. So this is how we can bound our errors. Okay. So we're going to use RK4 on our lovely equation that we've been working on so much in this section so far. We're going to analyze the error. Okay. So we'll start off with h equals 0.1, and then we'll talk about h equals 0.05. So to kick this off, I'm going to plug in my starting off points into my equation, right? So x is 0, y is 1. So 1 plus 0 times 1, right? So f of 0, 1 gives me 1 plus 0, 1, which is 1. Okay. K2 is going to be the same thing, but instead of being at 0, I will be at half of my step size away, right? So at 0.5 away, because my step size right now is 0.1, and then we can work out this thing as well, right? So here I'll be plugging in x naught plus 1/2 times 0.1, and my input for the K2 is my current y naught plus 1/2 times my h times the output I got for K1, which is easier than just plugging this all the way back into K1 like you saw in the last video. I'll just evaluate it and then plug it in, right? So I can take some more shortcuts here. So basically this means to plug in f of 0.05 and 1.5 into my equation. Remember, this is my f of x function, right? So plugging that in, I got y plus x times y, and that's 1.1025, right? I'm going to do the same thing for K3. So x naught plus 1/2 of h, so I'll have the same 0.05 value that I'm looking at, and my y value will be my current y value, which is 1 plus 1/2 times h, this thing, times my K2 times that. So instead of having 1 here, it'll have times that. Okay. So notice it's almost the exact same thing as K2, but for the output of K1, it's no longer 1. It's the output that I had for K2, 1.1.5. So I can plug in these values to figure out the values I'll be plugging into my f function. Okay. So this is what I'll be plugging in. So y plus x times y, and that's the value I got for K3. And I'll do the exact same thing again here, but instead of half of h, I'll plug in a full step size away, and then I'll have my step size times my K3 output I just got, and add that to 1. Okay. Right. So 1 full step size away, my current value plus my step size times my previous output for K3. So plug in 0.1 and have this value. Okay. So here I have y plus x times y. So that's 1.2218669375. So now I got K1, K2, K3, and my K4. So I'm going to take those 4 values and I'm going to throw them all together into this equation here to get my next approximation, right? So I haven't finished my first approximation. I just found the pieces I need in order to find that approximation. So I'll plug in my current yn, which is 1, 1/6 times my h, which is 0.1, times my K1, which is 1, plus 2 times K2, plus 2 times K3, which is on the other screen, plus K4. And when I add those all together, I will get my next approximation, right? So I'm throwing them all in here. Y plus 1/6 h, K1, 2 times K2, plus 2 times K3, plus K4. And that is my approximating value for Y1. So remember what we had from the last video, if you have been watching them in order. For the last video, for Eulers, we had 1.1, I believe. For improved Eulers with a step size of 0.1, we had 1.1105. And now we have several digits, okay? And remember, our exact value is somewhere around 1.1107 something. I never showed you the values because I always cut it off at 4 values. So for these remaining videos, we'll have more decimal places being shown, and we can come straight to our video. So notice how many decimal places I have current. So what I did was I basically, for all our values, I showed you as much as I need until we have 1 decimal place incorrect. So notice that these are very, very, very accurate, especially for the first step, right? We are very, very close to being correct. Even all the way to our last step, I have what? 1, 2, 3, 4, 5. I have 5 digits that are correct. Okay, so here I have 1, 2, 3, 4, 5, 6, right? No, it's still 5, sorry. I have 5 digits of accuracy. All of these 5 digits are correct, and then I start to have some error. So this is very, very accurate for a semi-large step size, right? This is h equaling 0.1 is fairly large, right? But I'm extremely, extremely accurate for that, right? So this is my end relative error. Okay, if I kept this as a percent, like I should, right, I would bring in the 2 decimal places. That's way, way, way less than a single percent of error, right? Very, very accurate. So when we do this for h equals 0.05, this is what we have. So look how accurate this is, right? That means that for this error, I need to put 8 zeros in front of this 3. So I have 8 decimal places of accuracy before I come to an error, right? So that is extremely, extremely accurate. If you notice, I can't even, if I were to write the whole value until we had error, I wouldn't have even been able to fit this up onto the screen, okay? So in order for me to put the actual error with all the zeros that I needed, I also would have ran out of room on the screen. So I had to write this into scientific notation, right? So notice here, we have at the end 6 decimal places of accuracy, okay? Because remember, you have to move it over 1 and then 6 zeros before you start, okay? So this is 6 decimal places of accuracy, which is extremely, extremely accurate, right? So it's not until this 7, right here. So these first 6 are identical, okay? So that compounded error that we get is very, very, very small. So RK4 is a very standard numerical method. Obviously, you're not going to be doing this by hand. To be honest, none of these methods really. You generally will have a solver or numerical calculator do these things for you, okay? Which is exactly what I did. However, you can't do that for the error. For the error, you have to calculate these by hand, okay? If I want to bound the error, I need the 5th derivative. Okay, and my 5th derivative of my solution function is this. So remember, the reason why I'm doing this function over and over again is because it was very easy to solve. And if it's easy to solve for an actual explicit solution, it's very easy then to analyze the error because I know what the actual error is, right? If I don't, I just have to rely on the fact that I know the big O notation, global and local truncation errors, for this, right? But if I have the actual values, because it's a solvable DE, I can tell you exactly what the absolute error is and the relative percent error is, okay? But if there was no solution, I would have to rely on the accuracy of these methods to give me a close enough approximation to build my rocket ship so that it doesn't explode, right? Or build my bridge so that it doesn't collapse, okay? So since this function again is growing over our interval, we're going to let C be the largest value in the interval of existence for my situation. Okay, so I found the 5th derivative so that I could bound my error. So if you see here, I almost ran out of room because it's so large, this polynomial here. So I have 1 over 5 factorial, right, times h to the 5th power, because that's the order of this method for the local truncation, right? H to the 5th, n equals 5. I have my my solution here, or I should just say my 5th derivative of my solution, and that will help me to bound my error, right? So the maximum error I should get here from one step to the next is 5 decimal places of accuracy, and I'm pretty sure that we have that, right? So from here, I have 9 decimal places to 9 decimal places. Sorry, 8 to 8 decimal places. None of these have even only 5 decimal places. All of them are more than 5, right? So in this, oh, sorry, that was for this one. Okay, So 1, 2, 3, 4, 5. So all of these are within what we would expect here. If not, they're very close. Okay. So again, this agrees with our calculations, and these are for I think I just did this on my own. Did I have this as part of the question? We just said to analyze the error, right? So I'm doing this bounds, right, for the worst case scenario, which is that my step size is 0.1. Okay, that's my H here. Okay. Now if I were going to just divide the two global truncation errors, okay, so this is from H equals 0, 0.5. So that's me looking at the actual value divided by the the absolute error divided by, okay, that's this, right? 0, 0, 0, 0, 0, 0, 0, 1, 3, 6. Okay, and for the other one, it's 8, 7, 6, 6, 5. So I'm taking both of those, okay, 1, 6, 3 here, and have the other one, and I'm dividing the two, okay, and that gives me about 0.064118, and what I would expect it to be is 1/2 to the 4th. Since my local is to the 5th, my local should be to the 4th. Well, 1/2 to the 4th is 0.0625. Very, very close. Okay, they pretty much agree with each other. Right, so 136. And this is 16378. So I think I divided them correctly, but I wrote the wrong one down. Okay. So which is what we expect for halving H with a global truncation error of 0, H to the 4th.